one of the first things that a chemist must do when he is studying a new compound is determine the simplest formula of this compound. Now, in order to do this, two different items of information must be known. We must know the ratio by weight in which the elements of that compound combine, and we must know the atomic weight of each of the elements involved. With this information, we can proceed to calculate the simplest formula of the compound. For example, assume that we have a 10-gram sample of a compound of carbon and oxygen. We've analyzed this compound and found that in the 10-gram sample we have present 2.729 grams of carbon and 7.271 grams of oxygen. This is the first item of information that we require, the weight ratio in which the two elements combine. In order to write the formula, however, we need to know the ratio in which the two elements combine by atom. And in order to convert the weight ratio to an atom ratio, we need to know the atomic weight of the element. A consultation with the table of atomic weights tells us that carbon has a weight of 12.01 and oxygen 16. If we divide the 2.729 grams of carbon that we have by the 12.01 grams of carbon in 1 gram atom, we find that we have present here 0.227 gram atoms of carbon. And similarly, 0.454 gram atoms of oxygen. Now, 0.227 and 0.454 are obviously in a ratio to each other as 1 is to 2. And this tells us then that the simplest formula for this compound of carbon and oxygen is CO2, which indicates that 1 atom of carbon combines with 2 atoms of oxygen. Now, in this film, we're going to examine the compound formed by copper and sulfur. We're going to determine the combining weight ratio experimentally. We're going to consult with our atomic weight chart to get the atomic weights of these two elements. Then we'll perform a similar calculation to the one on the board to determine the simplest formula of the compound of copper and sulfur. You should bear in mind throughout, however, that the two items of information which we require in order to perform this calculation are the weight ratio in which the elements combine and the atomic weight of the elements as present. In this experiment, we're going to first weigh carefully out a sample of copper, then combine it with sulfur, and then find the weight of the product. Now, in order to do this, we need first to determine carefully the weight of 2 small porcelain crucibles, because we're going to carry out this experiment in duplicate. That is, we're going to run 2 experiments all the way through. Now, the crucible on this left pan of the balance has been weighed. The crucible is sitting on the pan on the left. On the right-hand pan, we have a 10-gram weight. On the beam, we've placed a rider at the 0.4 of a gram mark. And then we've lowered this little chain here in such a way that the sum total of the weights of the 10-gram weight and the 0.4 gram rider and the weight of the chain exactly balance the weight of the crucible. Now, by lowering the door to prevent drafts from disturbing the balance setup, we note that the needle is right at the midway mark on the scale, and we can read the weight of the crucible from the balance. And it weighs 10.428 grams to the nearest milligram. 10.428 grams. And this weight should be recorded on your data sheet. This crucible has been weighed in an entirely similar manner. It's the crucible for use in experiment 2, and it weighs 10.361 grams. And that weight should be recorded also. After determining the weight of the crucible, we will now add a small piece of copper to the crucible, weigh both together accurately, and by subtracting the weight of the crucible from the combined weight, we may obtain the weight of our sample of copper. I've cut off a small piece of copper wire here, which weighs approximately 1 gram. And we'll fold this up into convenient size place it in the crucible. Then we'll replace the crucible on the pan of the balance and determine the combined weight of the crucible and the copper wire. The combined weight of the copper and the crucible has now been determined and is found to be 11.466 grams. 11.466 grams. And this should be entered on your data sheet in the blank for the weight of the crucible plus the sample. Similarly, a second piece of copper wire has been placed in crucible number 2, and the combined weight of that crucible and its sample is 11.522 grams. This value should be entered also. I've now placed our crucibles containing our weighed samples of copper on these two triangles. We'll place quite a large excess of sulfur in each crucible because any excess sulfur added will simply vaporize and be driven off in the course of the heating operation. We want to make sure that we have enough sulfur to react with all of the copper in the wire. So we'll charge both crucibles with sulfur. Then we'll place the lids on the crucibles, and we'll heat for a period of about 10 minutes, long enough to ensure that all of the sulfur has been driven off. Then we'll cool the crucibles and weigh them. And this weight will be the weight of the copper sulfide formed in the course of the reaction. We're performing this experiment in a hood because we're going to form rather large amounts of sulfur dioxide gas, and this is not pleasant to have around in an unventilated room. The crucible containing the copper and the sulfur was heated for 10 minutes in the flame of the Bunsen burner. It was then permitted to cool, additional sulfur was added, and the contents of the crucible were again heated for 10 minutes with the burner flame. Now the crucible has been permitted to cool to room temperature a second time. The material in the crucible has the appearance that you see on the screen. It's a black substance, still retaining the shape of the original copper wire. This material is now brittle, though. Our next step is to determine the weight of the crucible and the cuprous sulfide which it contains. We will now reweigh the crucible and its contents. Calculate the weight of the crucible by adding up the weights applied on various parts of the balance. On the right-hand pan, we placed 11 grams in large weights. We placed 7/10 of a gram on the rider. And by lowering this chain, we've added 41 thousandths of a gram from the chain, making the weight of this crucible and its contents 11.741 grams. The second crucible has also been weighed, and its weight is 11.832 grams. We will now proceed to calculate the formula for this sulfide of copper using the data obtained in this experiment. The weight of the empty crucibles are given on the board here. Crucible 1 weighed 10.428 grams, Crucible 2, 10.361 grams. The crucibles plus the copper, 11.466 and 11.522 grams. And by subtraction, we can calculate the weight of the copper used in each sample to be 1.038 and 1.161. Then after we added the sulfur, caused it to react with the copper, and removed the excess sulfur, we find that the weight of the crucible and the product was 11.741 and 11.832, respectively. The weight of the product can be obtained by subtracting the weight of the crucible from the weight of the crucible and the product, and this gives us 1.313 and 1.471 for the weight of the product in each case. Now we know that in this product of copper and sulfur there was 1.038 grams of copper. So by subtracting this value from this figure, we can determine the weight of the sulfur present in each sample of product, and this comes out to be 0.275 grams and 0.310 grams. Now with this information, we can proceed to calculate the percent of copper in the sample and the percent of sulfur in the sample. The percent of copper we'd obtain by dividing the weight of the copper, 1.038, by the weight of the product, or in this case 1.161 by 1.471. And we find the percent of copper in the two samples comes out 79.1 and 78.9. Now these two figures are not exactly the same, but considering the rather crude way in which the experiment is done, they represent a pretty close check. The percent of sulfur calculated in a similar way comes out to be 20.9 and 21.1. The average of the two values for the percent of sulfur then is 79.0, and the average of the 2% for the sulfur is 21.0. And we'll now use these figures in the determination of the simplest formula of this sulfide of copper. In our previous calculation, we found that in this compound of copper and sulfur, the weight ratios were 79 for copper and 21 for sulfur. This is our experimental result. This is the ratio in which those two elements combine by weight to form this compound. Now, in order to reduce these weight ratios to atom ratios so that we can write the formula, we must divide these two numbers by the atomic weights of those two elements. The atomic weight of copper is 63.54, and the atomic weight of sulfur is 32.06. In carrying out this calculation, we find that we get 1.24 and 0.655. Now these two numbers then represent the ratio in which the atoms of copper and sulfur combine. And I think it's obvious that this number is just about twice this number. Twice 0.65 would be 1.3 about approximately. So from this calculation then, we know that the ratio between these two numbers is 2:1, very nearly. And we may then write the formula for this sulfide of copper as Cu2S. Now, in order to carry out this calculation, as I said earlier, we needed two values: the weight ratios in which these elements combine, and this value we calculated in the experiment, and the atomic weights, which in this particular case we looked up on our chart. In this film, we've seen how we started with a piece of copper metal, accurately weighed and with the normal flexible properties of copper, how we placed this in a crucible, added sulfur, heated, obtained cuprous sulfide, an entirely different set of properties, and how we then proceeded to a determination of the formula of cuprous sulfide.